Having looked at the motion of particles and rigid body motion, now we will cover a very specific kind of motion that is very useful and has a lot of rich physics in it. It is known as simple harmonic motion or simple harmonic oscillation. And let us see how it comes about. Whenever a particle is in a stable equilibrium, that is, it is at the bottom of some kind of a well, so that when it moves, it always comes back to its equilibrium position, then I can expand the potential energy about that point. This could be any shape. About this point, let us call this point x0, and I am focusing on one dimension. Then u at a point x away from x0 can be written as potential energy at x0 plus the derivative of potential energy at x0 times x minus x0 plus 1/2 the second derivative of the potential energy at x0, this is also at x0, x minus x0 square, as long as x minus x0 is small enough, plus higher order terms. If x0 is the point which is of that of stable equilibrium, then the force which is the derivative of potential energy is going to be 0 at this point, and therefore the first correction that comes to ux0 is this term. If I retain only this term and drop the higher order terms, then I would be approximating the potential about the stable equilibrium point, something like this, something like a parabola, which is nothing but u x0 plus 1/2 some constant k x minus x0 square. So let us see. What we are saying is, if the particle is in some equilibrium position at some point, then in general I can write the potential energy about that point x minus x0 is equal to the potential energy at x0 plus 1/2 k x minus x0 square, to a good approximation, where k is the second derivative of the potential energy at this point, and since this is a stable equilibrium point or the minimum of potential energy, this is greater than 0. Let me for convenience now write x minus x0 as only x, that is in effect I am taking x0 to be 0 and ux0 to be 0. Remember, potential energy is always with respect to some reference point, so I am choosing my reference so that ux0 is 0. So I can now write the potential energy as ux is equal to 1/2 kx square, and that you recognize right away as the potential energy of a spring stretched by distance x. So the potential energy with respect to x looks something like this, which is 1/2 kx square. Therefore, if a particle of mass m is moving in this potential, its equation of motion will be given as mx dot is equal to minus d by dx of 1/2 k x square, which is minus kx, or mx double dot plus kx is equal to 0. So this is the simplest possible equation about a stable equilibrium point. Why I call it the simplest is because there could be cases where even the second derivative of the potential is 0, therefore correction would be higher order. For example, I could have a potential ux which is proportional to x raised to 4, or I could have higher order derivatives which are also important. For example, I could have ux is equal to 1/2 kx square plus, let's say, k1 x cube, and so on. If I neglect all these and I assume that only the second order is non-zero, then this is the equation of motion, and therefore this is known as the simple harmonic motion. So let us see now what we have is mx double dot plus kx is equal to 0. This is also the equation for a mass tied at the end of a spring which is oscillating on a frictionless plane. So the prototype of simple harmonic motion is going to be a spring mass system. With this mass m and a spring constant k, and you can already see that there are many examples where I can apply this as the first form of approximation to the real motion. For example, I could have a particle at the bottom of a cup, a clamped rod which is vibrating, a simple pendulum, and so on. So therefore this is a very good system and very useful system when we want to study motion about an equilibrium point. Let me now give you two examples of how the potential energy looks like and how we approximate it, and what the force on the system looks like. For example, I talked about particle at the bottom of a cup. A cup could be of this shape and the particle could be sitting here. It could have a very functional dependence on x which is quite different, but when I approximate this potential energy for small motion as 1/2 kx square, what I am doing is approximating the potential energy by this parabola. So this is how the potential energy looks when I am approximating this motion by a simple harmonic motion, and the force would be Fx is equal to minus kx. So when x is positive, I am approximating the force like this, and when x is negative, it's like this line. You see here that in reality the force goes something like this, and then it becomes slightly less in magnitude. Force goes something like this, and then it becomes slightly less in magnitude. But we approximate this as this line, and therefore as long as the motion is confined to this region, it is a good approximation. As a second example, let us take a pendulum of length L which is swinging about its equilibrium point. You can see when it is swung by an angle theta, the potential energy U as a function of theta is going to be given as mgl 1 minus cosine of theta, and therefore the potential energy is going to look something like this. It is minimum at theta equal to 0, then it goes like a cosine curve. And so on. However, when we approximate this as a simple harmonic motion, then the potential energy becomes mgl divided by 2 theta square, and therefore I am approximating this potential energy like this. This point is 0. So again you can see for a good range of theta, the approximation to the potential and the potential itself are quite close to each other. How about the force? force, again we are approximating the force to be a linear force, but as you go far away the slope goes down, and therefore the real force is something like this, and then it oscillates. So again, for a good range of theta, the force is linear in theta, and therefore simple harmonic motion is a good approximation for low displacements. In these lectures we are going to talk about the simple harmonic motion,